Okay, so far what we did can be summarized in few sentences. In the first day, we talked about a mixture of polymer chains. That's what we did. And then using random mixing approximation, we derived the free energy of mixing, which went something like a 2-component system. We had something like this. So in this, we had temperature as one of the variables, and chi, that depends upon temperature and chemical mismatch between these different components. But this is a mean field description.
So one question. So when I have a polymer and I'm trying to write down a Fourier-Nix theory, the counting of states is a really difficult challenge there. So is it like people assume that it's a mean field, like they are not seeing each other, excluded volume interaction, and these things are ignored when computing the entropy, change in entropy?
That's not true. They do. We do accounting for conformational entropy,
But,
right?
But yeah, I mean, I would like to know that a bit.
Are you sure? Okay.
So we should discuss that.
We could discuss that either offline or
Yeah.
today a little bit. Okay, let's keep going. Right. Okay, so we did this here, as Sandeep is saying, we did not account for any fluctuations, no fluctuations. We placed them randomly and counted number of ways of placing them, and that gave this entropy of mixing, which always favors mixing. And here we took into account only nearest neighbor interactions between type 1 and type 1, between type 2 and type 2, between type 1 and type 2. We did not think in terms of backbiting, for example. A part of this chain may undergo a conformational change, right, and then come back and interact. That correlation, long range correlation, we did not account for. That was in the first lecture. Right. In the second lecture, given this premise, we calculated the power of this mean field theory was the ability to calculate this thermodynamic stability of the system. So temperature, this is related to 1 over chi as a function of volume fraction of the one of the components. We had a coexistence curve like this with a critical temperature Tc and a spinodal curve like this. Inside this is completely unstable. Between the envelope of this yellow curve and the red curve, we have metastability. That was what we did in the second lecture. And we also showed the criteria for the spinodal decomposition, the limit of thermodynamic instability, the second derivative of free energy, secondary free energy that we calculated here with respect to the composition is 0. That was the criterion for this spinodal line. But on the other hand, at a given temperature and given composition, it will undergo phase separation to give me two phases, two daughter phases, one phase here, another phase there, in such a way the chemical potential of one component is same in these two daughter phases, chemical potential of the second component is the same on the at the same two compositions. Okay, that's what we did. We also, based on this, we also looked at some fluctuations in here about the critical temperature. That means, right, the very fact that we have fluctuations means that there should be additional terms. Nevertheless, we invoked this Landau-Ginzburg free energy functional, not worrying about the interface. We assume that there's going to be an interfacial tension, but the leading term of that lambda free energy is second derivative of this delta f by kt with respect to phi, which becomes 0 at the red point. And from there, and in fact what we did was we wrote this red curve, we had something like 1 over n1 phi 1 plus 1 over n2 1 minus phi 1 minus 2 chi. This is equal to 0 at this point, and this we call it to be A, and we wrote this to be 2 chi critical, chi sphenodal minus chi. Since the chi is the reciprocal of t, this went like t minus t, let me call this to be t sphenodal, t minus t sphenodal. That's the way it went. Right. So A is like a quench depth or the distance or temperature, distant temperature from the sphenodal point. Okay, that's what we did in the second lecture.
Sorry, chi should go at 1 over t, right?
Yeah, t will go like, yeah.
So okay, I mean.
Sure, let's do this. 1 over t minus 1 over t, yes, that's equal to Ts minus
Sure.
T, right. All right? Yeah. It's related to T minus Ts. And we also argued that as you approach this point, right, the scattering intensity goes to infinity. That's because it goes like 1 over A. We worked it out. This is Onfray and Zernicka, right, or free field theory if you listen to other talks, right. So this the intensity will diverge, and then depending upon, because the second derivative of free energy is going to be 0 here. This is my second derivative, that's going to be 0 at the red curve, spinal curve. So when we approach like this is going to 0, second derivative, reciprocal of second derivative, this is Einstein theorem, right. Reciprocal of second derivative is a scattering intensity. This is called a sum rule, that's what he showed, and then Woods and Zernicka demonstrated by using experiments. Okay, so that's what we did in the second lecture. And the third lecture, what we did was to bring a little bit of respect to this polymer. The polymer molecule is not just a bunch of sphere just randomly mixing. As Sandeep was trying to ask me the question earlier, it has a correlation. Okay, and how did we treat this correlation? The way we did that was to consider, to begin with, let me write for a Gaussian chain, then we can generalize this. For a Gaussian chain, if you have a chain like this, random walking chain, the radius of gyration of this chain goes to like square root of n times monomer length divided by 6, root of 6. Okay. That is like a ball of wool. The typical radius of this coil goes like this. Okay. And we wrote down in general this to be like n to the nu, proportionate to the nu. In this particular case, nu is equal to half for a Gaussian chain. And then what we did was, I need to use this in the rest of the talk. What we did was, this was due to Debye. What he showed was the structure factor which we measure in experiments, right, scattering intensity, right, if the incident wavelength comes in, incident beam comes in and hits here and scatters off, and hits somewhere here, it scatters off, and when they get scattered, then there is a constructive interference, and then you measure that intensity. That scattering intensity as a function of the scattering wave vector k, which I defined in several times, k, that is proportional to the structure factor S of k, that is proportional to 1 over n, that is equal to 1 over n, summation over I, summation over j, e to the I k dot the position of the ith monomer minus position of the jth monomer. But the important thing is, this turns out to be, this is averaged out, scattering, I am averaging because this is all dancing around. This turns out to be equal to 2n k to the 4 or g to the 4 e to the minus k square. You have it in your notes already, so you don't have to copy it again. Something like this. But the important thing that comes out of this is, this goes like n to the 1 minus the 3 k square r g square, sorry, 3 k square r g square by 3 here, plus etc. or 1 over k square. K is scattering by vector. When k is large, I am looking inside the coil. When k is small, I am looking outside the coil. If I want to know the size of the polymer and the mass of the polymer, my probe that I am going to look at, this one should be, the probe length should be larger. Otherwise, I will not be able to measure. If I want to measure the size of me, if I have a yardstick only this much, that is not going to measure my 1 meter height. I need a yardstick which is bigger than this, right. That means k should be small. So, that is what we do here. This is when k times Rg is smaller than 1, I can get Rg, measurement of Rg, which I told you. That's the way people measure. That's why in every laboratory, commercial instruments, everything, they use this idea. On the other hand, if I go to length scales shorter than radius of gyration, k Rg is greater than 1, then I am interrogating the substance in this short length scale, and then I get 1 over k square. Okay. What if I of k goes like 1 over k square, that means the density, this one is density concentration correlation function. Therefore, the density variable from one point and from the other way, if you do the Fourier transform, rho of k goes like 1 over k square. Now, let us do the Fourier transform this, rho of r goes like 1 over k square, Fourier transform that goes like 1 over r, apart from 4 pi and everything. So, if even for a Gaussian chain, if I look at, say I go to somewhere here and look at how the monomer density is changing with the distance, it goes like 1 over r. Okay. Exactly. That means the monomers are correlated and they have a long range correlation. Just almost like having a charge, electrical charge, and the field is felt far away, even though, right, the density is falling off like 1 over r. This is why we say the topological correlation of a single chain is long range, or the chain connectivity itself results in this correlation. Okay. So, somehow we had to bring this up into our formalism to accurately describe my free energy of this mixture.
What was the density?
Local density, yeah, density, monomer density.
How is it if rho goes up as 1 over r?
Say it again, please.
If rho goes up over as 1 over r, how does it ensure long range?
How is it what?
How does it ensure long range correlation? I would have thought that C of r going as 1 over r would be.
Yeah, local concentration, right. Let me draw a cartoon here. So, if I have a chain like this, right, and let us say this is the radial distance r. If I plot monomer correlation function, that I choose one monomer here, what is the probability I am going to find another monomer at certain radial distance r? If I plot this, that is going to go like radial, right, r 0 is going to go like this. Okay. For short distances, you know, you will not see anything. So, maybe I should plot like it will go like 1 over r. Far away, you will not see any monomers. Very close to the location you chose, the density will be high, but then when you go away, it is going to fall off like 1 over r. Compare this with a globule. If you had a globule folded protein, then the density profile would look like this, flat, until the radius of imagine a steel ball of steel, up to the radius it will be flat and nothing outside. In contrast to that, you have 1 over r like a long range correlation. Okay.
This is density correlation.
This is density correlation. So, I am writing rho 0, rho r average, but a rho 0 I am just picking one point. Okay. But this is important to know how the correlation function is taken, how they are correlated, right? The density is falling off. But in general, this is 1 over r is for a Gaussian chain. But in general, depending upon the interactions, which we did a derivation in the last lecture, right, depending upon the correlations, you will have a different value. Nu does not have to be half, it could be a different number. typically in good solutions where you have extra volume interactions, that becomes like a 3/5 for approximately 3/5, for example. And we also said this 1 over k square actually is 1 over k to the 1 over nu, fractal dimension, and fractal dimension is 1 over nu. Okay. Therefore, this r then would go like 3 minus 1 over nu in general. When nu is equal to half Gaussian chain, that becomes 2, 3 minus 2 is 1, and it is not necessarily 1 over r. It would be a different power law depending upon the conditions. If they are charged, depending how much salt you have, they will be different. Now, going back to an earlier comment, suppose it is collapsed object. If it is collapsed object, nu is equal to 1/3, right, because Rg goes like into the 1/3, Rg cubed, which is volume, is proportional to mass. When nu is equal to 1/3, you see 1 divided by 1/3 gives me 3, 3 minus 3 is 0. So, it is a number, there is no correlates, it is highly correlated until the radius. That is my blue curve. This corresponds to nu is equal to 1/3, this corresponds to nu is equal to half, and somewhere in the middle depending upon your experimental conditions. Okay. And somehow we need to bring this up, and we know how to do it. It is not somehow, we do the technology I introduced in the last lecture. You write the Hamiltonian and work it out, and then you will calculate the consequence of these structures. Comments? Any question?
Yeah, this rho of r, this is density profile or this pair correlation?
They are the same. They are the same. So, we write a rho of r as concentration at some location C, concentration r, right. That is proportional to rho of r, right. You fix some average density corresponding to the same. With respect to that, how the other one is varying with distance. Okay, so, right. Any other comments? Okay, this is what we did so far. Any other comments?
So, one question. So this structure factor is always proportional to rho k density in.
Yeah, it's a rho k. Yeah, rho k square. It will turn out density. The structure factor is a rho k square, rho square, monomer correlation function, because one rho will come from one sum, summation over I, e to the ik dot ri. That's your density in Fourier space. Right, and then the other one is complex conjugate of the density in Fourier space. So, rho k, rho minus k average is your structure factor. Right, the density, right, the density, I write in and erase it. Rho of k, let me write rho of r. Rho of r is equal to summation over I in this particular case of 1 to n, a delta of r minus ri. Right. If a monomer is at the location r, it will count to the density. If it is not there, it will not count. Okay, what is rho of k? Rho of k is a Fourier transform of this summation over I 1 to n dr e to the ik dot r and delta of r minus ri. That is equal to, do the integral, right, delta of r, wherever you see r, you put it in, get rid of this summation over I from 1 to n e to the ik dot ri. That is what appeared in here, e to the ik dot ri summation over I. That is rho k. And the other one is a rho minus k, because of negative sign here, because it cannot be imaginary. The structure factor cannot be imaginary, it should be real. So, you take the complex e to the ik dot ri, complex conjugate of that e to the minus ik dot rj, you take the product, and that your scattering intensity. That is the way we do. Yeah.
So how would semi-flexible?
What?
How would semi-flexible nature of the polymer affects
Well, you could guess it from here. Semi-flexible, I did not do the derivation. Of course, we have the technology to do the derivation. Nu would be something like 0.8, right? Because 0.6, 3/5, roughly 0.6 is the extra volume chain, and the rod is nu is equal to 1. R is related to n proportional to n as 1. So, semi-flexible chains would be somewhere between 0.6 and 1 depending upon the extent of semi-flexibility, right. So, it could be 0.8, 0.9, 0.7, right, but never 1, it turns out it is never 1 unless it is really a short double stranded DNA. Okay, so what I like to do today is to equipped with all this information, I want to go and go down below the coexistence curve. So, here is a homogeneous phase, right, and I want to go down, right, into this. That means I am going to quench the system underneath this yellow curve, and I can quench into the unstable region or I can quench into the metastable region depending upon the composition. And I like to address what is expected if I quench here or I quench there. It turns out depending on where I quench, the system evolves in a particular way. If I quench here, it is going to evolve in one particular way. If I quench here or quench there, it will evolve in another different way. But nevertheless, at the end, I will get the same answer, same result. The same, suppose I quench to this temperature here, right, I will always get these two daughter phases. Whether I quench here, 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 it does not matter. But the pathway of reaching the final state will be different. Okay? There are two distinct pathways, and that is what I want to address it today. Okay. Before I go further, right, I need to know a little bit about the free energy, because if I am going to quench a system, the way the system is going to evolve depends upon the free energy of the system. But so far I wrote only the free energy only for this part, only mean field part, and somehow I had to bring this part into this one, going back to the earlier question, right. And I started doing this, but we ran out of time. So, let me summarize what we did before. I think I'm going to erase this, right. If I had a chain like this, dilute solution, when I make the concentration to be higher, then I have interpenetration. So, there is a concentration, polymer concentration, above which this interpenetration is going to take place. That concentration is called overlap concentration. This is for C greater than a concentration called C star. This is overlap. That is a concentration at which the chains are able to overlap between them. They are able to interpenetrate. For concentrations less than that, the chains are going to be alone, more like a dilutes. They are lonely. But when you keep on increasing the concentration and when you reach this limit, then they begin to interpenetrate.
So only one chain, if it penetrates with the others, we will consider it as a penetration or condensed system.
No, I think this overlap concentrations for the whole system. All chains are interpenetrating.
How do we define this interpenetration? When do we call two chains are interpenetrating?
It's not two chains, right? So imagine I have many chains, right? I have n chains. So let me take a box, right? There are n chains, right? So this is one chain in here with some radius gyration. Another chain is in here. Another chain is in here, on and on. And here another one, on and on. Another one, on and on. And another one, on and on, right? When the concentration, right, roughly there are prefactors which one has to work out. If the concentration is such that there are n chains and there are n segments, all right, there are little n number of chains, n segments, okay, that is the total number of monomers divided by, right, volume of the chain in such a way it is n chains times the volume of this, volume of each chain, that is say Rg cubed. apart from 4 by 3 pi and everything. I am not writing down, all right. Let me put it like this. Okay. So, I take a volume Rg and they are essentially compact, right, in this concentration, then the total volume is proportional to the volume of each coil times the number of chains, and the concentration defined in terms of mass by volume. That mass is, there are n monomers per chain and there are little n chains, and Rg we know Rg goes like n to the nu. Therefore, this C star, this will be the C star. So, C star would go like n power 1, n power 3 nu. So, this goes like n to the 1 minus 3 nu roughly, and prefactors can be obtained. Okay. That is the definition of C star.
I was asking because if suppose these are linear thread-like things, if they are
Yeah.
still like for concentration less than this C star also, they could interpenetrate like two threads going like.
That is not the way we define, right? Because this is a coil like, right? This is a coil, right? More like a ball of wool, all right. You are not talking about a rod like. If it is a rod, right? If it is a rod, then you have liquid crystallinity, there are also other complications, right? We are not talking about that. This is a flexible chain which has a certain radius, right? And then when you bring multiple chains together, they are going to be packing until they begin to interpenetrate. If you increase the concentration more than that, then they will begin to interpenetrate.
So, like if the interaction is tuned such that this ball has, like you said, the density profile falls off as 1 over r. So it will retain its spherical kind of shape throughout
Until it interpenetrates.
until it.
Yeah. All right. Do you go to market to buy things, vegetables?
Yes.
You do? Do you buy apples?
Yes.
Take a bag of apples. What do you see?
Apple.
Apples.
Yeah.
They are all packed.
Yeah.
Okay. Now take a large number of flexible polymers.
Yeah.
Do you think they are going to be like that?
Mm.
No, they will interpenetrate.
Yeah.
Why?
That
Why? Why would they interpenetrate?
because the ends can go.
Because they will gain entropy.
Yeah.
They are able to adopt enormous number of conformations by interpenetration, right? Unlike apples, you just pack them, right? Imagine yourself made of a bunch of balls, in contrast with polymers, right? Polymers are able to interpenetrate. When they are able to interpenetrate, why? Because they gain lots of entropy. That's favorable.
Yeah.
So, yeah.
What I was saying is that interpenetration is possible even for less concentration than this C star, because the threads could go from one sack of wool. The threads.
That's not the way it works, because the translation entropy that can avoid and go and explore the whole volume is more. When in the very dilute solution, right? Here is one polymer chain, another polymer chain. Why would it try harder to interpret? Instead, it will wander around. Only when you increase the concentration, they cannot get anywhere except to interpenetrate and gain entropy, right? So that's why we define this. Anyway, since we are kind of slow now, today is the last lecture, right? Right, Sandeep? Right. So yeah, but still keep asking. I can hang around for extra time if you have stamina. Okay, so what I did was I showed in the last lecture, when you have interpenetration, then the interaction between segments, right, between two segments, which is responsible for this nu, that gets screened. All right, we talked about Edwards screening, right? The extrude volume interaction gets screened. We had a nice discussion with Devayan this morning. Right, they get screened. So what is the consequence of this? So in a good solvent, right? In a good solvent, the chain is swollen, so that nu is 3/5. But when I increase the concentration in the same solvent, same good solvent, when I increase the concentration, the chains begin to interpenetrate, and then when I measure experimentally with neutron scattering, measure the radius of gyration of one labeled chain, same chemistry, same solvent, but in a dense system, it is a Gaussian chain. That means that the interaction, the intra-chain interaction now is screened by interpenetrating other chains, and therefore, this is like between me and Devayan, right? our interaction is being screened by this gentleman.
By Sandeep.
Huh?
By Sandeep.
Sandeep. He doesn't want to. Doesn't want me to talk to him. He screens, right? If he's not here, we talk. Same thing. So it's a screening, and then we did a calculation. Yeah. Sorry.
So for overlap concentration, you are considering here all the chains are like homopolymer kind of. If they are not, if they are heteropolymers, then say like as you are saying, the screening effect will statically come into play. Say negative, positive, they might like interpret it more maybe in a lower concentration as well. Right?
It's possible. It's entirely possible. So yeah, it is entirely possible. But it's entirely possible. So when you write like this, the chain has not seen yet. Okay, I'm still writing this configuration, right? I have not written this yet. So this is going to be indicator of when that's going to happen. The effect that you are talking about is going to happen at concentration higher than this, not below. Right? Okay. So what we showed was this: the simple argument we did, and I did not mention the technical name for that. The technical name is random phase approximation. And you will see this in any field in condensed matter physics. People say RPA. That's what people call, and that's what we did. So what we did was we took all the tree diagrams, tree structures, interactions, right? As a consequence of this, what we found was there is a correlation length. That is, if I have this something like this, then I have a distance. I have distance in this interpenetrating system. There is a distance here along which the monomers are correlated, just like the correlation that I am talking about. So instead of 1 over r, now it is screened only over that distance. I have correlation. Beyond that distance, other chains come into play, and that 1 over r correlation is wiped out. In fact, what we showed was the effective interaction of the r goes like v, right, and 1 over r e to the minus r over c. That's what we wrote down. Something I'm not writing all the 4 pi's and everything. Originally, you would have 1 over r. That 1 over r interaction is now converted into something Yukawa type, screen interaction type. And clearly, this interaction is extrude volume interaction only up to a distance comparable to c. For distance larger than that is the zilch. It's not going to c. Okay. And then we showed in the last lecture, we showed that c goes like, for neutral polymers, it went like a concentration power minus half. For charged polymers, it went like c to the minus quarter. That's what we did in the last lecture. Now, this is RPA. But when you have this, the tree-like approximation we made may not be enough, right? It may not be enough. So you need to do proper calculation for strong fluctuations. Instead of this, suppose with strong fluctuations, if you have this, it turns out, which I'm guilty, right? C goes like c to the minus 3/4, and we know the numbers in here. And for charged systems, it goes to c to the minus half, and we know these numbers. That number we know, that number we know. Okay. All that I'm trying to say is, you have to trust me that there exists a technical methodology, which is what we do in the other campus, right? Tomorrow and day after, day after tomorrow, and then you can calculate these correlation lengths for these highly fluctuating topologically correlated systems. Okay. And why am I even taking a burden to mention this to you? The reason is, when I look at the free energy, right, this free energy by kBT, I have the mean field part, which we did there, plus a fluctuating part. That fluctuating part goes like 1 over 24 pi. The pi always creeps in, you know, you guys know that, right? It is a magic pi. Pi c square b, sorry, c cubed b, where this c is the correlation length. Okay, this is, you can take it as a theorem, and it is derivable, and there are references where you can derive, right, and it is a mathematical beauty to derive this, right. If you are interested in bringing mathematics, theoretical physics and mathematics to beautiful polymer physics, soft matter physics, living matter, if you want to do that, you will enjoy doing this calculation. So, the fluctuations are contributing, and this C depends upon the concentration of the polymer, right. That is volume fraction, related to volume fraction of the polymer of some kind. So, therefore, when I write the free energy of the system, it depends upon the concentration of the polymer and of the chi parameter, and all the electrostatic interaction go into this early part, and then plus this also depends upon Beerem length, which I mentioned. All those things will come into play. So, that is our starting point in composition of this coexistence curve, right. I can make the statement the chemical potentials are the same, and I showed the calculation for the simplistic case, how to do the calculation, but when you have these things, and it may be necessary to do numerically, okay, because of the, you know, it is not analytical function, right. This goes like c to some fractional power, so you may have to do analytically, okay. Then you will have accuracy in comparing with the experiments. Okay, that is a road map of this is your starting point, and you use the thermodynamic principles of equality of chemical potentials for the coexistence curve, and the second derivative of free energy going to 0 with respect to composition to dictate a spinel curve. Okay.
So
If I ask one thing, that the fluctuation is in psi, which has only the concentration part. Temperature is not there.
Oh, temperature appears there. Yeah.
I mean, the way you have written, temperature is coming only in delta.
Prefactor. Yeah, there is a prefactor here.
Oh, there is a
Prefactor. Yeah. And for the Coulomb cases, it is the Beerem length. The dielectric constant appears here. Dielectric constant depends on temperature, that appears there. That is why you may have to do numerically for a realistic problem for biomolecular condensates. You have to do it properly. You have to first learn this and execute it properly for your particular system, and then compose it. Yeah.
So if I, rather than polymers, if I consider just particles, point particles, in that case, how does this get modified? Or more importantly, like for the kinetics, what features will polymer give you, like if a nucleation growth and all that I do not get from a particle?
Yeah. Okay. This is an excellent question. Could you please wait? Yeah. Could you please wait? So the question is what's the distinction between particles and this one, right? In a similar to the previous question, if it's a particle, nu is equal to 1/3, right? Nu is equal to 1/3. So where is C star then? Nu is equal to 1/3, right? It doesn't depend upon molecular weight at all, because that C star is not small numbers. C star is really the whole system. Random closest random packing 0.63, whatever that number is, right? That's what happens, right? But more importantly, when we look at the phase diagram, how does the topological correlation appear in distinguishing the kinetics of simple particles to the structured particles, structured molecules? And that's the reason why I am preparing myself to, I'm reminding you folks, that's the reason why this part I reproduced, because we are going to use this to bring about what's happening there. All right. Okay, so
just one question. What strong fluctuation mean? Topological strong fluctuation meaning?
it means more like still there is, let's take polymers and water. That means still the polymer chains can adopt lots of conformations.
Those fluctuations.
Yeah, that's highly fluctuations. But if you increase the concentration more and more, there is not enough volume for solvent, there is not enough solvent, and then they fluctuate, but they don't fluctuate that much. Okay?
Going to dilute basically.
No, it's too concentrated. In dilute is a heavy fluctuation, and then increase the concentration, high fluctuation, and then no fluctuations, right? And RPA traditionally is valid for weak fluctuations in all fields of condensed matter physics. right? All fields are conserved matter of physics, RPA corresponds to weak fluctuations. In fact, when we make measurements, you observe this result in the semi-ideal conditions, and you observe that result in very high concentrations when you do neutron scattering. Similarly for charge systems. Okay?
I have just, I want, why are you calling topological correlation? Why, what is the
It's a
meaning
chain
of
connect.
topology?
Oh, that's a good question, right? Because it has a dimension, right, and it's a connectivity.
Yes, dimension and connectivity, and even if you destroy something, that will be, still will be like that.
Yeah. It's a permanent topology. Yeah, it's not like some creation and annihilation operators chopping the chain and making them again, right? Like unlike there are lots of worm like micelles, they would not be topological because they make and break. This is a nomenclature, right? Yeah. People sometimes do not want to call topological when they simply say chain connectivity, but it is indeed topological for the reasons that we talked about.
Because in a topological, generally we find some kind of a invariant number, right, corresponding to that.
Talk about invariance, yeah.
So there may be some invariant number.
Well, if you have one chain here and then bring another chain, how many times it winds around, right? That's a topological invariant.
That will be like whatever you do, it will be this.
It will be there, yeah. But that is more like an Aharonov-Bohm effect. In the quantum, it's the Aharonov-Bohm effect, and that's what we will have here. How many times? So if you have a chain which is being knotted, right, you could use Alexander polynomial as an invariant or Jones polynomial as an invariant and tau. That's a topological constraint. That's the reason why people use this. At least I use this. Okay, so who wants to? Let's take a vote. You want me to do this one first or this one first?
Either you one is first.
You one is the first. Since you are the first to say and you is the first. Okay, yeah. So the first, the early bird, catches the worm, right? That's the phrase. Okay, so I'm going to erase this. Is that okay? But I want to keep that one. And I'll erase this too. I'll keep that one. Okay, so let me go here, right? Let me go somewhere there, and then I'm going to quench like this. I go there, and that's the point I'm going to go. And I want to ask a question of what will happen, right? Somewhere here at the early, before I do the experiment, I go there, and I want to write concentration of the polymer or your entity at some location R to be equilibrium value without any fluctuation. So plus a fluctuation, as we introduced in the last lecture, day before yesterday, right? There is a mean field value and there is some fluctuation. Now, that fluctuation gets bigger and bigger when I go down in temperature, right? That's what we talked about, and that's that result. And then you measure that fluctuations using the Wonst and Zernicka methodology, scattering intensity methodology. That's what we did. Okay. When I suddenly quench it, I will have that fluctuation here, right? But that is unstable. What it wants to do, it wants to make two daughter phases with one phase with that composition, another phase with that composition. So something is going to happen. So in order to understand this, let's look at the kinetics. There is a d phi r by dt is equal to negative divergence of flux. This is the conservation of mass, right? This is conservation, negative gradient of flux. What is flux?
So that's the chemical potential. You are going to write in the
Okay, a gradient of chemical potential, negative sign, and there is a coefficient before. I mean, professor is not allowed. Anybody knows what the coefficient is? Okay, you can say mobility. We call this to be Onsager coefficient. Okay, Onsager was a great genius. You guys know this, right? The guy who solved a two-dimensional Ising model exactly, only his brain and paper and pencil. Onsager coefficient. In simpler cases, that becomes a diffusion coefficient, and this equation is called Fick's diffusion law, Fick's law of diffusion.
So when you say special cases, it becomes a diffusion. Like when is it?
When there is no cooperativity, only one particle.
One particle.
Yeah.
And we know a relationship between this and a corresponding single. I don't know how to think about that, but is a
Corresponding what?
like a single particle.
You just wait. Wait. Okay, so what is the chemical potential? I told you, right? Chemical potential is d delta F by d n1, right? So this is more or less, this is proportional to d delta F by d phi 1. Okay. Okay, so I could rewrite this, right? I could rewrite using this. I could substitute this expression phi of r into this, and let me work in Fourier space, because we always do scattering. When you do light scattering or neutron scattering, X-ray scattering, we work in a K space. That scattering wave, that's a Fourier transform, right? So let me work out the Fourier transform of this continuity equation, but take care of the linear response, only fluctuation part. What you get is a d psi k by dt is equal to, going back to this, negative times negative positive, and then I have this lambda, there is a del square. The Fourier term to del square is a negative k square. Therefore, I get a negative lambda k square, right? And the gradient of that would be delta f in a Fourier space, maybe delta psi k. Okay, that's the equivalent of Fick's law, or non-equilibrium time evolution of fluctuations in general. And I also told you delta f in the last lecture by kBt is equal to half summation over k resolving various modes, and that is a plus kappa k square times psi k square within simple Landau-Ginzburg theory, without RPA, without doing any without doing very complicated calculations. And this is what I showed in the high temperature phase. Let's start there to begin with, and we will work out all the other consequences.
Kept up to the second order.
Sorry?
Kept in Ginzburg-Landau, you kept up to second order.
Second order, only up to second order. All right, and then A we wrote down to be equal to 1 over n1. I think we wrote on phi 1 plus 1 over n2 phi 2 minus 2 chi. Did I write down somewhere here? Maybe not. Yeah, here. Sorry, I forgot already. That's my A, same thing, and that goes like this. A goes like T minus the Tc. Right? I'm coming up from here, or if I come this way, suppose I come off quench, I come here. That instead of Tc, I will say T Spinoza, Ts, subscript S, T minus Ts. Okay. So I could generally use a T minus Ts if you want, because at the critical point, Ts is same as a Tc. So the prefactor here A, not prefactor, the coefficient A, the leading term in Landau theory, is a measure of the distance of temperature from the spinodal temperature. And this is the interfacial term. I told you about kappa being an interfacial term. Okay. Now, this is the place, this is a time that I should pay respect to an earlier question from Sandeep, the distinction between particles and the polymer. Okay. Let us go to this one. If I have Debye structure factor like this, which has the k dependence, this must somehow appear in this expression A. It must appear. The reason why it did not appear here is we are taking k is equal to 0 limit, the thermodynamic limit. When k is 0, I am talking about an infinitely larger system. Therefore, I can write down this expression. Okay. So, if you do this, right? If you do this in the context of RPA, let's do RPA, then the structure factor S of k, right? Now for the mixture, now I'm talking about structure but not one particular chain, it goes like this goes like 1 divided by phi 1 S device structure for the first component. Maybe I should not write, let me write I of k. No, yeah. This is for the whole mixture. This is for the first component k plus 1 over phi 2, the device structure for the second component k, and then plus minus 2 chi. So, this formula that I am writing here becomes generalized into this one, where S d1 k is this expression. S d1 k is this expression, and for the first component, degree of polymerization, number of monomers could be capital N1, radius gyration could be Rg1. For the second component, it will be N2, Rg2. So, in general, you could, I am not going to write explicitly, but you get the idea. So, you get this is my structure factor. You also know the structure factor is the correlation order parameter correlation function, right? Structure factor is, right, the average of psi k square, similar to we wrote a density correlation function, similar to that for mixtures, for intermingling mixtures, it will become average of square of this psi k. That is my structure factor. That you can calculate as a reciprocal of this. Okay. So, if you do, again I am interested in k small, right, because we are interested in thermodynamic phase transitions, right. So, k becoming small, this turns out to be 1 over n1 phi 1 plus 1 over n2 phi 2 minus 2 chi, right. Then I can expand this S1 k. I already told you S of k goes like n1, now in this case that's my n1, and then the denominator 1 minus k square Rg square by 3. So, I am going to put in the numerator, I will pick a term k square, 1 divided by 1 minus will give me 1 plus k square. So, that will give me here, that will give me plus k square, and you can tell me Rg square goes like L square n1 divided by, there is a 3, Rg square 6, and then there is 3, that will be 18, and then I have here n1. I take this, right, this is going to be 1 divided by the square bracket. So, therefore, when I bring this to the right hand side, when k small, I will bring 1 plus 1 times n1, right, you do this, then this whole thing is the denominator. What you get is k square n L square by 6, and there is a 3 here, and then 1 factor n will cancel, and that will give me this term. Just do the arithmetics. Similarly, for the other component. So, therefore, I could rewrite this n, okay. Similarly, for that component k square L square n2 divided by 18 n2. So, if you have particles, this will not come about, right, because the structure factor, form factor of a sphere is 1. There is no k dependence, right. There is really no there is no k dependence, right. Okay, if that is the case, then what I have is taking this in here, this kappa, which is related to the surface tension, right, interfacial tension, that kappa is equal to, we are now deriving kappa based upon the structure of the polymer, and that is equal to, you can write, there is a phi 1, there is also phi 1 here, and this is phi 2. So, what you have is 1 over 18 times 1 over phi 1 plus 1 over phi 2. Okay. Because I am comparing k square, because I am picking from the structure of the polymers components, even within RPA, I am picking a term which goes like k square. That means in free energy, that is square gradient term in free square gradient space. So, therefore, I collect all the coefficients, it becomes like this. This is important because when you have a droplet, right, which we are going to see, the interfacial tension is going to play a role, because with the concentrations low, right. So, you write phi 2 to be 1 minus phi 1, 1 minus phi, this is phi, right. If the concentration of the polymer is low, right, 1 minus phi is comparable to 1, this is 1, but this is going to dominate, this is going to be very large. So, it creates lots of interfacial tension in the condensates, entirely due to entropic origin. Entropic origin, because we calculated how is this, how is that term coming about? That is coming about because of the topological correlation of the polymer chain. Okay. And that is the difference between particles and polymers. Interfacial tension is augmented by the topological correlation. Okay. Given this, okay, that is the setup. Okay. So, let me look at this one. How is this going to evolve with time? Okay. This is only with the linear terms here. I did not do anything else, right, only with the linear term. So, how is this going to evolve? That is trivial to do with the first order partial differential equation, simple differential equation. So, if you do this psi of k, right, at time t and psi of k at 0 time, and average it out. This is what I want to do. Why? This is what I measure. The structure factor that I mean, the intensity I measure now is a time dependent structure factor, time dependent correlation function of the order parameter, right. So, that is what I want to calculate. How do I do this? So, I can solve this simple equation, d psi k bring, oh sorry, this is equal to minus lambda k square. Let us do this calculation, and that is going to be equal to, right, given this, we take the derivative, function derivative, I have a plus kappa k square times psi k. Okay. So, using this, I am taking the function derivative and I get that one, and that is a linear thing, because d psi k by dt is proportional to psi k. Therefore, d psi k by psi k, that is d log psi k, is equal to whatever I have here times dt, and integrate it out. If you do this, you get psi k square, this is equilibrium, times e to the omega k some rate times a t is exponential, where omega k is equal to minus lambda k square a plus kappa k square. That is it. If I am writing fast, you have to stop me, because I have a bad habit of writing quickly. Okay. Did I do it right?
So, omega k is a positive for all k.
Let us wait here. Let us do it. Let us do it. I am going to plot omega k. Okay. Let us plot omega k. Okay. So, omega k. So, I am going to erase it. I need space. Okay. May I erase this, please? Can I erase it? Yeah. Let us plot omega k. Okay. So, Onsager coefficient, that is always positive, negative sign always negative, square of k positive, kappa interfacial tension must be positive, k square is positive. Now, let us look at A. I wrote down to be T minus Ts. Okay. Now, temperature is here or here, temperature is here and Ts is there. So, T minus Ts is negative, because I quenched it. Okay. So, therefore, A is negative when I quench it. A is negative and this is positive, this is positive, this is negative sign, and this is A is okay. So, let us look at small k. For small k, this is not going to be that important compared to A. For small k, this is not going to be important. Therefore, this is a negative number, and then another I have negative number, positive quantity. This is quadratic in k, negative, negative, positive, quadratic in k. So, what happens is this is going to increase like this for small k, but for large k, this is going to dominate over this. This is going to dominate over that. That means this is positive times that is positive, there is a negative sign. So, it is going to go like a k to the 4 with a negative sign. So, it is going to go down, crash down like k to the 4. So, what will happen? It has to turn around, right. This means even in the weak fluctuation limit, right, we have a spontaneous selection of some rate of fluctuation growth, right. So, this is positive, 0, negative, and we can calculate this. When this is going to be 0, let me call it the critical value of k, that is going to be what? I think a over kappa square root, okay, because this is going to be 0, right? Yeah, a over kappa square root. And when k, there is some number, this a depends upon the quench depth, and kappa depends on the interfacial tension, which in turn depends upon concentration. Okay. Given this combination of concentration, molecular weight, right, and quench depth, if I am looking at a large k means a small wavelength. Small wavelength is large k. That's rate of that fluctuation, rate of growth of the fluctuation is negative. That means they are going to be killed. But on the other hand, for smaller k, less than this value of Kc, that means large fluctuations, they are going to grow. That is positive. So, according to this description, which is correct description, large wavelength fluctuations are cannibalizing smaller wavelength fluctuations. The bigger fluctuation, long fluctuations are growing with a positive rate. They are growing, and the other small wavelength fluctuations are decaying. Okay, these have lots of implications: sociology, economics, the way politics is run. And we know in personally, some of us are rich, some of us are poor, and there is zero sum game, right? And you know how this happens. Right. So based upon this, you can work backwards to say, how could I become here instead of there? You work it out. Take it as homework. Okay, so what's the consequence of this? Then I put this back in here, right? Then this fluctuation will grow. So I measure scattering intensity, I have kT as a function of k, and let's do at the different times. At the early time, very, very early time, right? Omega k is going to be what? For smaller value of k, it's going to grow. For large value of k, is going to go down. So that means you are going to see an intensity like this. Only for because up to positive, right? It will be intensity will go like this, because that's where you are seeing growth. But for higher values of k, they will not see any intensity. So you wait a little longer, same thing will happen, but except now with longer, this t is larger than before, and it's exponential. So a little longer, it'll go like this, and little longer, even higher intensity, it will go like this. That means the peak position would not shift in the scattering intensity as a function of time. Peak position will be at one particular value, but intensity will be going like crazy. Okay. So if I plot I of k, maximum intensity, k max, right? No, let me not do that yet. Okay, let me do this.
So
Okay.
again, going back to the point of this polymer picture. So kappa will be impacted, as you said. So then essentially, if kappa is much larger for polymer, then the RC, the position at which you cut, will be different between polymers.
Right.
So, and is it possible to now somehow detect in experiments where this polymeric feature comes out?
Yeah, sure. Of course, indeed. So you can shift. The phenomenon will be the same.
Yes, but
Right.
those are
You have designing ability to orchestrate the navigation of fluctuational growth. Particularly Mother Nature plays this game with the biomolecular content. That's why there's a plethora of biomolecular condensates, and then with the small changes in sequences of everything, you can play magic. But at the risk of repetition, the burden on us, or the opportunity and also luck that we have, is to be able to do these things very cleanly, and then bring this picture and then decorate the sequences of the polymer and then go further. Because this is a ground floor. This is something that we must do first. I am talking to younger people. We must do this first. Okay, and then rushing to computation or modeling, whatever. Right? These are basic things. Okay, but now if you wait long enough, you will see peak like this. Okay, the maximum has moved to the left, because when the fluctuations are growing, I cannot afford it to be stuck only with the psi k square term, because now the magnitude of psi k becomes larger, the fluctuation becomes larger, therefore psi cubed term will be important, psi fourth term will be important. So, I have to take that into account, and that is beyond the scope of these lectures. But if you do this, then eventually you get the ultimate phases. Okay. So, let me plot k max as a function of time, logarithm of time. What will happen is, for early times, right, k max would be somewhere here, flat. This is called an early stage of spinodal decomposition. This is a very early stage of spinodal decomposition. K max is independent of time. Then k max moves towards the left, and in fact, one could identify this moving with a slope of a negative 1/3. K max, that is, the domains are growing with the time like a t to the 1/3 power law. This is called again this guy Landau, Schleier's dynamics, Landau, Schleier's mechanism. Basically, the droplets are coalescing, and some of them are breaking up, others are coalescing. When you look at that kinetics of association dissociation, you get this 1/3 law, and eventually it will become slope of -1. This is called hydrodynamic limit. People believe hydrodynamics is playing a role, because now we are talking about large length scales, and now the droplets are moving around, and the hydrodynamic flow is correlating all these things. So, this is all experimentally verified. Okay. This is universal. The description that I am making here in terms of spinodal decomposition is universal. Any system, right? You can think of a birth of stars, right? In a galaxy, a bunch of stars, they grow, they die, all those things, right? Same thing. That is the way we try to describe them. Okay, so are you done? Is that okay? Now let us go.
Time dependent Ginsburg-Landau you have taken.
This is time dependent Ginsburg-Landau.
And time dependent RPA also.
Time dependent RPA also. Yeah, right. This is here time dependent TD-LG, time dependent Landau-Ginsburg. So, I started with Landau-Ginsburg in this is a Ginsburg term. So, as I mentioned, this was introduced by Ginsburg in the context of superconductivity, but the interfaces are everywhere. Whenever you have interfaces, you must have that term, right? And it turns out the first person before Ginsburg, the first person who talked about this interfacial tension is Gibbs, of course.
1905 books.
Sorry?
When did he talk this?
That was in I believe 93, Gibbs.
But he published a book in 1905.
Who?
Gibbs?
Willard Gibbs? Yeah, it takes a while to write the book. I don't know. This is a great place, right? This is this is a great place for mathematics, right? We call all this Ramanujan Hall, everything, right? Hardy was one of the mentors of Ramanujan. Hardy had said, "Young men prove theorems, old men write books." Okay. So he wrote the book much later. Okay. Anyways, so let's go to the second part, and since we are kind of running late, but I want to complete this part. Is that okay? What time do you have?
I think we have this part.
Can I finish this? So, let me try to be brief. Okay, I am going to erase this. Is that okay?
Just a small question. I thought that scaling 1/3 was named Lifshitz.
It could be. It's in the Lifshitz book, right? But
I think it's Lifshitz-Slavsov.
is it Lifshitz-Slavsov? It could be Lifshitz. Yeah, Lifshitz-Slavsov. Some people give credit to Landau and Lifshitz. Lifshitz wrote the book. People say it's a Landau. Doesn't matter. I'll make you happy. LLS, Landau, Lifshitz, Slavsov.
And this -1 scaling you see even in
CGI. Yeah, it's even in small molecular systems.
right. So even in the absence of fluid,
It's also what?
even if the background fluid is, I mean, even in the absence of fluid, the scaling might.
Yeah. Okay. Right. And then the Lifshitz, there are brothers, two brothers. There are two Lifshitz. One Lifshitz is a great polymer physicist. The other Lifshitz is this guy. Okay. This is the older one. Okay. So let me go to the second. This is going to be again a very universal kind of thing. And I'm going to be, in the interest of time and also my perception of your background, I'm going to make it very simple. Okay. So here the mechanism is proposed that since it's a metastable, I'm quenching into metastable state. What does that mean? That means it still remembers that it was the previous thing, right? So in the case of spinolo decomposition mechanism, see here I started here, some fluctuations like this, and then some fluctuation like that, and then some fluctuation like this. Eventually that led to, right, a concentrated phase of phi double prime and phi prime. Okay, phi prime and phi double prime. It is very more complicated, the dilute and dense phase, right? That's what happens. In contrast, this is spinolo decomposition. In contrast, we are going to talk about nucleation growth. Right away, a daughter phase is born. That daughter phase has its equilibrium value. So in other words, you'll have one droplet here, another droplet there, another one there, another one there, another one there in the solution. Okay. And if I want to plot this density profile, this is concentration, then this is a droplet. This is spatial location, right? This is spatial location. It is one droplet with phi double prime, right? Another droplet with the same component, like a tiny one like this, and then a bigger one like this, right? On and on and on. They are being born randomly, and they are being these are nuclei or baby nuclei or embryos of the real phase, real equilibrium phase, in contrast to these simple fluctuations. Okay, so if that's the case, let me consider one such a droplet and see how that can be formed. Let's assume for simplicity, it's a sphere of radius r. Okay, and what is the free energy of formation of this free energy formation of this droplet? Let me write in kT. All right, in units for kT. That's equal to, let's do it. The reason why this is formed is it's a thermodynamically favorable for it to form. That means it has a negative sign, and volume of this is 4/3 pi r cubed. And what is the free energy gain in doing this? Let me write this to be delta G, little g. And that delta G, of course, is related to, right, Tc minus the T, for example, T coexistence temperature, right, that is this temperature, right, this, suppose I quench it here, I quench it there. This is my T coexistence temperature according to the curve, but I am going down there. This is the temperature. So T coexistence minus T, that's the driving force. This is positive, right? This is positive. And with a negative sign, that's a gain in free energy. This is the one that is responsible for formation of the birth of this nucleus. But whenever you do this, there is a problem, right? The problem is I had to pay a penalty to create an interface, because I am separating by force, I am separating a rich domain here and the poor domain there, right? So I am creating this. So therefore, there is going to be interfacial tension, and that is equal to 4 pi r square. Let me write interfacial tension with sigma instead of kappa. Okay, very simple. This is really a high school kind of math, right? But the physics is very important. Now let me plot this as a function of r, f over kt, kbt as a function of r. And let us do the same game again. When the interfacial tension is positive, we know that. When r is small, r cubed is weaker than r square. Therefore, this is going to dominate, and it is going to dominate so that this quantity is quadratic in r, positive. So, it is going to go like this. And eventually, for large r cubed is going to dominate over r square. With a negative sign, this is going to be strong but negative. So, obviously, it is going to come down. Please recognize that I am writing this graph for free energy as a function of radius of this nucleus. Previously, I had a curve like this one, that is with the rate of growth of fluctuations with respect to scattering wave vector k, right. There are two different quantities, except although they look similar. So, this means what? Suppose I make a baby nucleus with some radius r, right. To make her grow, it is going to be hard, because in order to increase r, I have to pay energy, I have to pay penalty, it is going to be hard. And if I go here, it has a tendency, suppose I made it has a greater tendency for it to go down, shrink, instead of going up. So, if I by fluctuation, suppose I make some droplet of this radius, right, this radius, then the chance that it is going to dissolve is much higher. That is what will happen. But on the other hand, if I cross the barrier r star, suppose I go beyond r star, if I made it, the chance that it is going to survive, that means it is going to grow, is much higher. So, this is what we call nucleation barrier, right. There is a barrier, nucleation barrier. You need to cross that barrier for this droplet to become a viable droplet. If it does not cross, then it is going to dissolve back.
Let's say you also have something like crowding agents in your solution. In that case, will there be any deviations from this classical nucleation?
No, not necessarily. It all depends on free energy.
So, I mean, it will always follow this whenever.
We quench in the metastable system. Yeah. It could, it's very complicated when you have crowding agents, because this, I'm talking about what is called homogeneous nucleation here. When you have heterogeneous nucleation that can promote the both of these nuclei due to interfacial interactions and complexation, etc. I'm not going to talk about that today. Yeah, but in principle we can do it. Okay. Okay. So let's calculate r star. Who wants to do this? R star is looking for the minimum of this, it's the maximum of this one, and I can do this r star. Can somebody do it in your head? I am just minimizing this. Yeah. Okay. And please notice this. This is again a very loaded quantity. And this is going like 1 over delta t, 1 over delta t. So, if you do a shallow quench, delta t is small. If you do a shallow quench, then the droplet that you need to make must be much bigger. Droplet that will survive has to be bigger. If you do not make a bigger droplet for deep quench, it is not going to happen. So, if you want to make, this is very profound information in terms of biomolecular condensates, right. If you want to make a droplets, then the key variable is this quantity, how much quench, which in turn is related to all this chi c minus chi c, molecular weight, all those things we talked about, all those prefactors come into play. If the quench is large, then you can nucleate them, because the size that you need to make is small, therefore you can keep on going. Okay. It is kind of counterintuitive. right, because higher temperature you will be able to make it easy. No, it's the other way around. Right. Okay, so calculate the free energy barrier for this. I take this value, substitute back in here. So the F star in kT, I don't know, that's a 16 pi by 3 sigma cubed delta G square. I'm pretty sure that's what it is, because I know that it's related to the volume, right. You can do the arithmetics, right. Put this back, take this, put this back there. Okay. It's some number like that. But again, the important thing is 1 over delta T square. So, if the quantity depth is small, not only you have to make a bigger droplet, but the barrier is also very large. When delta T is small, the nucleation barrier goes to the sky. Right. So, in order to make these droplets, you need to have delta T reasonably not small. It should be reasonable, not too small. So, if you want to make measurements, you need to, or if you want to do simulations, so you should not just do arbitrarily. You should design your simulation in such a way you go to that delta T is large enough. Then you will see, otherwise you will be waiting in your computer for a long time. You can go home to some place and come back, right.
So that means your delta chi in this mode, right?
Say that again?
The delta chi, I mean, whatever chi you are changing, if the inverse relation, if I can.
Yeah, yeah.
Which means just with slight modifications, like post-translational modifications, you can tune all these things properly.
Probably, and that's why we get diseases. The post-translational modification kills us.
They are not big changes.
No, it's very delicate, quite delicate, very quite delicate. Delicate it is, life is delicate. Yeah. Yes, but still we are resilient. Yeah, we can do it. All right. Okay. So, I think I think that this is a good place to stop. Right. And then it grows. Once you pay a price to cross a barrier, and then you make a stable nucleus, which will grow. Right. And you could, for the growth, you could write all the fancy mathematical techniques, so like a Fokker-Planck representation and the various things, in nonlinear, Boltzmann equation. So many techniques are available to look at the growth kinetics. Okay. But in summary, I must say, this is where again Lifshitz comes in, Landau and Lifshitz comes in. The growth dr by dt, in the early stage, after the viable nuclei are born, in the early stage it goes like square root of t. Okay. And a little later, dr by the late stage, it is a early first nucleation. And then in the growth, there are two possibilities. So the early stage of growth stage, it goes to square root of t. Basically, it's a diffusion like. And then much later, they are collaborating. Then dr by dt. I should not have written like this. Excuse me. I should have written r of t. Growth grows like this. Sorry, excuse me. R of t goes like t to the 1/3. Okay. The very early stage of growth, r goes to the square root of t, and that should not be surprising to you, because we talked about this Einstein's law. This means r square. It's more like a diffusion. R square goes like t, and that I think the theory has that signature of the Einstein's diffusion. That's how this happens. But at a later stage, there are cooperativity, collaboration, then you get t to the 1/3. That is like our Lifshitz slides on. The late stage of nucleation growth and late stage of spinor decomposition follow the same law. Okay. So, I am basically done, right. We started in a humble way from here, right, and we predicted phase diagrams. We looked at how to make measurements, how to interpret the parameters and how to design them. We did that. And then we brought structure of this polymer chains into picture, and then we looked at the implications of that, and then using all these things that we have mustered, tied them together, we are able to look at the time evolution of these structures. Right. One thing I did not point out here is, in the last lecture I told you, if you have a charged system, even in equilibrium, we have spontaneous selection of structure, micro phase separation, we talked about it. In a similar way, when you look at the kinetics, what happens is you have a cutoff. of a wave vectors, where instead of looking at in the case of simple system macro phase separation, all wavelengths below all wavelengths larger than a certain value will grow. But when you have micro phase separation, that is not true. Only intermediate wavelengths will be selected and they will grow. The large wavelength fluctuation will not grow, short wavelength fluctuation will not grow, only the wavelengths corresponding to the micro phase separated structures, only they will grow with the time, and they get locked into that structure forever. And that is the thing, and that's we can do this at another time, maybe next year. Yeah. Okay, with that I am done. Please ask me questions if you have any.
So generally this is an example of a phase transition, right? So phase transition, a classical system of this, not quantum phase transition, this falls under the Ginsburg phase transition where symmetry breaks, right? So in this case, what is the symmetry analogy which is breaking there, and we can construct. So in the language of symmetry, degree of freedom will be doubling in this phase, right? And the way what you learn today is that you start from there and just evolve the system you can study. But in a quantum condensed matter system, if you want to come back, because symmetry is broken, degree of freedom has increased, so we have to develop all this RPA and everything. It will take a matrix of structures. So what is the difference here?
Well,
you are capturing everything.
Yeah, this is good. Let's say, the nice thing about these systems is the translational symmetry, translational degree of freedom, that symmetry is not broken, right? So whenever the order parameter undergoes a discontinuous change, that's the symmetry we are talking about. It's a symmetry, the order parameter could be plus and minus, right? When that is broken, we say classical phase transitions. In that context, that's the way we do it. So the order parameter, the sign of the order parameter has, that's a symmetry. That symmetry is broken. Yeah. This is also true with the van der Waals gases, also true biocondense and all of them. But I think, please, the question is a very important question, right? The question is, the description that I have given is universal for all first order phase transitions. Birth of the universe, we write same expressions. I am sure you do all. Birth of the universe, how is the universe born? We write it this way. Baby universe is born, and if she is healthy enough, she will grow. And then there will be structures inside, depending on what else is happening. How is star born, and on and on. And how is a biocondensate born, right? So this is very universal. It's the basic stuff, and it's a responsibility of any physical or physical scientist to know this stuff. Cold.
So which book? You have two books, right? First book, and which one?
For these things, probably the second one.
Second one, the latest one.
Yeah. Right. Any comments, questions?
I have one question that you mentioned about overlapping concentration, right? So can we say that
tomorrow?
I'll meet you tomorrow. Yeah, no escape from me for 2 more days. Thanks to you, and thanks to you. Sorry, keep going.
So in overlapping if it causes the overlapping concentration, then the phase separation can happen, or it's not related to phase separation?
It's not related to this. Yeah. It's not related. Yeah. Purushottam, questions, comments?
Well, I'm just wondering that it didn't strike me before that we talk about universality in second order transition. And the universal is very well defined, and you can talk about it from RG concept. But it's the first order transition, that again on kinetics. So I was just wondering, and I was thinking that it didn't strike me before. I mean, of course, you get that it will go 1/3 at late times and all this, but yeah.
Yeah, it's universal. Yeah, I know.
But is there any, just like the one that you get in the second order transition, the universality, here is it that well defined?
Same thing. Because, well, this point is second order phase transition, as you know. The critical point, it's a critical point. Yeah, that's except that point, everything else is first order phase transition. As soon as you go down, first order phase transition, even infinitesimally away. and then you have all the consequences, everything that we talked about.
But I think that you carefully chose the also, you called it TS and you never called it TC.
For spinor decomposition, yeah. Not in the books though, but that I do.
Yeah, I mean, people.
I know, they are very
it's
sloppy.
It's very sloppy.
Very
and
sloppy.
They're very different, and one should be extremely careful
Yeah.
with defining critical points.
Yeah, that's a critical point. For the audience here, critical point is second order phase transition, because the order of the transition is defined in terms of which derivative gives a discontinuity. In the second order phase transition, the second derivative of free energy gives a discontinuity, and the first order, the first derivative like specific heat, volume, things like that. Okay. Yeah, any question? There was another hand. You had
No, I was just wondering, it's a very nice question, that if you have the concentration very large, very high, and the chain length is long, then I will get a situation where there will be a lot of frustration. I'm in a kind of glassy kind of situation when I will not see this. So, that limit is not coming into the equation. So obviously you are not going to that limit. So that is the kind of understanding.
Well, even not quite, right? Because remember the Onsager coefficient, that's the transport coefficient. That has interactions with all the neighbors and also diffusion, right? The collective diffusion, and that's where it will appear if you do it. But on the other hand, for polymeric systems, it's very easy to get into glassy state,
Yes.
right? And it takes very long time.
Yeah.
In all these things, we are talking about annealed cases. That is, they are able to explore the whole phase space. The kinetics is taking place. It's still the system is ergodic. Yeah. If it's not ergodic, then that's their problem, future problem for those people.
What is the minimal element that you need to add to these polymers to actually see the glassy behavior, or you can see it even here?
See, it depends upon whom you are talking to, right? To me, if the barrier for one conformation getting converted to another conformation is significantly higher than thermal energy, right? Then it will make a glass. Okay, and in workout the other way around, similar to this one, the exponential of that barrier for between two conformations, e to the that barrier divided by t, you can calculate the time, e to the that barrier by kT, that gives you time. If the time is age of the universe, it's a glass, right? It is not. It could happen even at room temperature. It could, in our labs, we see that in aqueous systems, room temperature, right? And it doesn't change. It doesn't. The system is frozen, glassy. Water, aqueous polymeric system at room temperature, they are frozen because the barrier is too high. Because another thing about polymers is they can easily, because of conformation entropy, you arrest the conformation entropy, suddenly the barrier goes up. All right. So that is a very hand waving argument. Okay, what is the number, right? Are you willing to wait for a year and then say it flows, or wait for 10 years to flow? That's the answer.
So basically, you have to have an observation time scale.
You have to have an observation time scale, and then you define a quantity. That's the way they define glass transition time, fragility, and everything. All those things they give an observation time. If
Otherwise, there is no way.
There's no way to do it.
It has to be practical.
Yeah,
kind of.
yeah. For that particular, from that perspective, in terms of English, we can say everything is a glass. Because your observation time is a picosecond, so it's not a glass, you can say, but it's a glass in principle.
We see this in simulations. All
Yeah,
the time.
yeah. But simulations are deadly. You have to be extremely careful. Simulations, right? We do simulations, right? So we know painfully, we know what not to do. Seriously, because it gets stuck. Okay. Yeah, please.
It's only a concern if you're in the
Say it again.
phase.
Say it again.
This barrier is only a concern if you're in the nucleation phase. If you're in the spinodal region, then you're not worried about this barrier.
Correct. So, okay. See, people say for the spinodal decompression, the barrier is negative. Okay, because it's spontaneous. There is no barrier, right? It is spontaneous. So there is no. That's why I wanted to emphasize when I showed a graph like this, not for free energy. That was a rate of growth. It looks dangerously looking very similar, but this is for the free energy. For the nucleation, there is a barrier. For spinodal decomposition, there is no barrier. Spontaneous growth. Okay, but the spontaneous growth is such that Rich gets richer at the cost of poor getting poorer in spinal decomposition. In nucleation growth, it's not that the case. The nuclear growth is everything that's born is healthy. It's healthy means right composition, but the size may be too small. Okay, and in that particular case, this Lifshitz slice off. That's basically the cannibalization. There is a bigger droplet or eating up smaller droplets and getting bigger. That's how that 1/3 law comes about. And this also, in another words, is also called evaporation condensation mechanism. Some of them are condensing, others are evaporating, and that's the way people describe these things. That's another a brutal way of saying that is cannibalization. Right, but
so, I mean, perhaps one can also get an intuition from the original free energy, the thing that you have, because there, if I plot it, I have these two wells, and depending on where, so the corresponding line where you get the spinodal and the binodal, you can say that it's perhaps easier to kind of go to the other one, like to actually phase separate compared to if you are close. So
sure.
That is also some intuition, perhaps.
That's right. That's right. That's the reason why yes, indeed. That's the reason we invest a lot of time about deriving this and making a mapping between the derived result with this one. So I illustrated for the simplest situation, right? But you could take this methodology for your system and then do it, right? And then you talk to your experimental colleagues, to make the measurement in the right place. Right? If you suggest an experiment to somebody and then if you give the wrong parameter space and the experiment won't work, then they'll say, oh, your theory is wrong, right? Because they're not looking at the right place. Okay, and that is our responsibility to tell this is where to look at.
Since you are talking about the kinetics, if I start from the unstable state and wait for the droplets to form and note the time, and if I start from the metastable state, so which time will be greater?
That's a very good question, right? All depends upon, see, I did not talk about the growth, the prefactors in here. I did not tell. I said this is what is going to happen. I did not tell exactly. That all depends upon how the molecules are going to be transported, right? And that in turn depends upon the composition, where you are. Somebody important about glassy thing, where you are, and also depends on temperature, right? And that's the one that dictates the relative speed of the process, right? It's not like this versus that. I think if the molecules are much longer in one system compared to another system, the longer one is going to take place very slowly. Right? Yeah. All depends on the prefactors. Yeah.
So this radius r of the droplet, does it have any kind of dependency on the constituent, say like the polymers Rg or the end-to-end distance?
Of course, indeed, because that they all appear through this delta G. Of course. That has a personality.
So if we know the end-to-end distance or Rg of a polymer, we can calculate its radius, right?
This is compared to radius gyration, this droplet is very big, right? That has many polymers inside.
I'm asking because like if we can calculate the concentration to form this droplet.
You can calculate because you can write delta G in terms of your concentration. So delta G, see, look, delta G I am kind of telling in terms of temperature, right? Delta T. Instead of this, you could also tell in terms of supersaturation, in terms of concentration. You can keep the temperature but change the concentration. If the saturation is higher, concentration higher, it will precipitate. It will precipitate, it will make a droplet. Or instead of temperature or polymer concentration, you can play with the salt concentration.
Yes, that you mentioned.
Yeah. So these are the variables through which you could create these new droplets. But fundamentally, it all depends upon your delta G.
I have one very naive question. So if one looks at systems that forms, let us say.
Say it again.
If one looks at a typical system that forms by molecular condensate, so any chemical condensate, the area within the spinodal region, and you compare that area of the metastable region, typically which one do you think is bigger?
Well, I do know the case of symmetric cases, right, the spinodal area is bigger. But if it is asymmetric, that one polymer is longer than the other polymer, then the metastable region will become bigger, because it gets skewed. It is the way I have drawn this a cartoon, symmetric. Like if it is asymmetric in terms of molecular weight, it will be skewed like this. Then metastable region will be longer. Depends on the system. But the thing is, you can calculate it. You know, you can calculate it. Okay.
So I had a question. So there are some experiments which people have done where, if there is a background mesh, your droplet, diffuses. I mean, it doesn't become one big droplet, but you see you do see some multiple droplets, and that's where it stays. So is there a way to account for this, in this picture or equation that you have written down?
Well, the Landau-Ginzburg theory that we have talked about, right? You could do that theory in a random media. So, the phase transitions we are talking about, Landau-Ginzburg phase transition, you could repeat this calculation in presence of random media, and then you prescribe the characteristic of the random medium in terms of some mesh size, right. Then as you can intuitively expect, the fluctuation will grow only up to that mesh size, and beyond that it is going to be cut out. So, then you can incorporate that in the quencher random media, then you can tell more. Yeah, you can tell more. But if your random medium is annealed, that is, the mesh size is dancing around, it is not only one, still you could do that. Yeah, still you could do that. Yeah. But there is a technology.
But that will change the entire picture also.
Yeah.
Because there will not grow, because it cannot grow.
Yes.
So we have to just, at some point it will percolate.
Percolate, or it will arrest,
Yeah.
right, it will arrest, it will poison. These are the kind of things, right, depending upon what temperature you are making the measurement, because your correlation length depends on temperature. Then there is a commensuration between the correlation length, thermal correlation length of phase separating system with the geometrical correlation in the background medium. So, you have to work, but it's fun. We can do it. Yeah. Okay, I think we are done, right. Thank you, folks. Take care.
Yeah.